This is Dr. Carroll, and today's video is about binary search trees. Before we get into implementation, let's talk about the abstract data type of a binary search tree. What is its interface? Okay, so it needs to provide the same function, a lot of the same functionality as a binary tree, except that it needs to preserve the three properties for each of the nodes. First, that all of the nodes, all of the values, the value for node n has to be greater than all of the values in the left subtree, and we're calling that T sub L. Furthermore, the value of n must be less than all of the values in the right subtree, if any. And furthermore, that the subtrees, the children of n, are binary search trees as well. It's a recursive definition. So often, the items in the nodes are classes, and that that's implied that each node has a search key. Well, what if we wanted to store a person or say a DNA object in a binary search tree? Well, let's look at keyed item class here. Here we have the keyed item. It's a templated class so that we can take any key type here, any key type. And we have a constructor, we have a getter, we have a setter, and then we have a protected type here, the key type. And that's all it is. All it does is basically hold one value, and it's meant to be a unique value. Okay? So back to our question. So if our binary search tree could then store keyed items, how could we store a person or a DNA object? Well, the answer is inheritance. So, for example, if we had a person object here, and we'd want to have person inherit from the keyed item class. Now, it's templated, so we need to specify how we want to template it. And let's just say for a person, we're keeping track of their name, an M number, and email string. Okay, so now that we have the person constructor, we need to call the keyed item constructor in the initialization list and pass it the M number. Oh, copy paste there, my bad. This is supposed to say M number here so that it'll compile. And the name we're going to populate in the private data member for person, or protected data member for person, and email again is going to be another protected member. So the point is, here in the initialization list, we're going to call the base class, and we're going to pass it in this parameter M number, and you can just pretend that says M number. Sorry about that. Okay. That's how we can store things. So let's talk about searching now. So for a search, we would have a function called something like a search, where we're going to pass in a node pointer. Let's just assume we're using pointers for the implementation of the binary tree and not an array-based one. And we also need to know what the search key is, and it's going to be of key type. Okay. So first, let's talk about some pseudocode. So search for the search key. That's here, this parameter, in the node pointing to by node pointer, if it's valid. And so we have our if here, if it's valid. Else, if it's not, else if the search key, if the search key is less than the node pointer's key, then we're going to search the right subtree. Otherwise, we're going to search the right subtree. Okay, so that's pseudocode. Now let's see it in skeleton code. So first we want to say, if the node pointer is empty, well, then we're going to say we haven't found the item. But if it's not empty, then if the search key is the same as the node pointer's key, great, we found the item and we can return that. Otherwise, if what we're looking for is less than the search key, then we need to go to the left subtree. We need to search on that. Notice the recursive call here. And otherwise, well, it's a binary tree, so there's only two possibilities for children. That means it's got to be greater than or equal to, or sorry, it's got to be greater than, and that means the right subtree. And there we have the searching method. What do we need to do to convert search into retrieval? Well, just add a return type and return statements, and there we have it. Okay. Let's look at the BST header file and implementation file, specifically looking at the retrieve functions. This is available in the class website to download. So here we have the binary search tree header file. We're going to take into account tree exceptions and tree node. It's going to be defined elsewhere. We have our constructor here. I'm going to go through this quickly. I'd like you to go through this file on your own to really let it soak in and learn a lot from it. Okay, so here we have search tree retrieval. We need to template here. The search tree retrieval, and here's in the header file. We're going to take a search key, and then we're going to just assign. We're going to pass by reference a tree item which we can populate, so we don't have to do all the returns. That's another way to do it, and that's what it looks like in the header file. Now, if we go over to the implementation file, we're looking for retrieval. And here we have it, and oh, wow, all it does is call retrieve item. Okay, well, let's look up retrieve item. That was pretty simple, and you'll find that this is a common thing here. Retrieve item is protected and not public because look what's being passed to it, a tree pointer. Okay, so that's an implementation issue and not a publicly available issue. So this method should stay out of the interface. And then if we look for retrieve item, insert, delete, retrieve item here, we have the pointer. So this is our node pointer. If it's null, there's a problem. We couldn't find the key. Otherwise, did it match? Great, then let's assign the reference that we passed in. Let's populate it. Otherwise, we're looking to see if it should be in the left subtree, and we'll recursive call on retrieve item, not on our public interface method, but on retrieve item. Otherwise, it'd start over again at root. And then otherwise, we're at the right subtree. It's fairly simple, actually, and that's all retrieve item right there. Has it not been found? Is it in the node we're currently visiting? No? Okay, then do we go left or do we go right? And that's as simple, that's all we need to do for that. Okay, there's a beauty in simplicity. Okay, so now inserting. Let's look at an example here. Okay, so if we had let's look at an example here. If we have these food items stored in a tree, pasta, flour, beans, oats, wheat, sugar, and we're searching for cocoa, where would it be? Where would cocoa be if we were searching for it? So here we have this tree that has some food items in it, pasta and flour, beans, oats, sugar, wheat. So if we were searching for beans, how would we find it? Well, we would come here and say, hey, is it here? No, this node is valid. It doesn't contain beans, and beans is less than pasta. So then we come down to flour. It's valid. It's not, this node's value is not, this node's key is not beans. So then we come down here. Is this node valid? Yes. And oh, we found it. Great. And so that's how we can recursively apply this to find different nodes. Now, what if we wanted to insert? So let's come back to this example. And if we were going to insert, for example, cocoa, where would we put it? Well, it'd be easiest to insert it as a leaf rather than trying to move things around. So we have 2 leaf options here, 2 leaf options here, 2 leaf options here, 1 leaf option here, except cocoa can only go one place to preserve the attributes of a binary search tree, which is that all of the items in the left subtree have to be less than the key, and all of the items in the right subtree have to be greater than the key, and the children need to be binary search trees. So cocoa can only go one place. It has to go to the left of pasta, has to go to the left of flour, and it has to go to the right of beans. So cocoa can only go right here. That's the only place it can go. What if we wanted to insert, say, rice, to have a little bit more complete picture here? Where can rice go? Well, rice needs to go to the right of pasta, but the left of wheat and the left of sugar. It's the only place that rice can go. So what did we end up doing, basically, to figure out where this went? It was the same thing as if we searched for it and found its correct place. Okay, so let's look at some skeleton code then. If we were going to insert an item, we had a node pointer and the new item we wanted to put in. So we're going to base this off search. So first, is the node we're currently pointing to at null? If it is, that means that we've reached a leaf node and that we can create a new item here. Otherwise, we haven't reached a leaf and we want to find out, do we go to the left and then we need to insert the item moving to the left, passing down, or do we need to go to the right? And it's really that simple, okay? Let's look again at the BST files, this time for insert. I believe insert was up here. So insert here, we're going to pass in a reference to the new item, a reference so that it's fast, and we might throw a tree exception. So insert, the search tree insert has all of insert item. Again, notice how that was common. You'll notice that we do the same thing for delete here. And what that does is, look, this is an implementation specific item that should not be in the public interface. So now we go to insert item, we're going to take a pointer and we're going to take the new item, okay? And we're going to take a reference to the pointer. So if the tree pointer is null, then we found where we want to insert the leaf and we create a new one. Well, we need to try to create a new one because we're doing memory allocation and it may fail. So we create a new node and we're going to pass it the new item, but its children are null. And then we're going to assign that to tree pointer, okay? And because it's a reference, we're going to update it and it's not just a copy of it. So then that way, if it wasn't a reference, then we would have had a copy of the pointer and we would have had to gone back up the tree to the parent and assign it. And that would have been a lot more complicated for what if the tree was empty, etc., etc. So we're going to try it. We'll catch bad allocation here. And if we catch it, well, then we'll throw the tree exception with a message, okay? But so if it's not a leaf, if we haven't figured out where it goes, then we see, hey, the new item, is its key less than the current key's item? If so, then let's go to the left, insert the item in the left subtree. Otherwise, we're going to insert it in the right. And there we go. Again, a beautiful recursive implementation.